you. Welcome to a brand new episode of Reverse Engineering. So, herein we have seen how to solve the Ohm's law and to check the current directions and voltage polarities. Now, in today's lecture, we will be interested in solving some of the problems. What are the techniques we have learned? So, let's put those techniques first. If you are new to the channel, please like, share, and subscribe the channel. And before moving to the lecture number third, please visit lecture number 1 and 2. Let's take straight away a problem from gate examination. So, this has appeared for 2 marks. Yes, in a gate examination, and let's write the problem, and we'll be also studying the resistive bridge technology today over here. So let's start the problem. So this is the circuit, plus minus E, and we have a resistance, 1 ohm resistance, and we have another 6 ohm resistance. So this resistance is 1 ohms. There's a 6 ohm resistor over here, and there's a current I that is going through here, and 1 ohm, 6 ohm, and another 1 ohm resistor over here. So this another 1 ohm resistor. Then we have a 4 ohm resistor connected in shunt, as you can see over here. This is my 4 ohm resistor. Via the 4 ohm resistor, there is 2 amps current flowing, and then I have one more 1 ohm resistor connected over here. So this resistor reads 1 ohms. 1 ohm. So this is a resistor over here that is reading 1 ohm. So if we see the circuit pretty carefully, so what we notice in this particular circuit is that we have to calculate, we have to find the value of E and I. So in order to find the value of E and I, so how do we start with the circuit? Now if we notice this particular area, so there's a resistor over here. So this is a 1 ohm resistor that is connected. Again, for your benefit, I'll be drawing this. So if we notice this area over here, so again let me draw it one more time so that it becomes a little bit clear. This so this is a circuit somewhat okay. Let's take it to a next level. Yeah, let's take it to a next page so that we get a better understanding of this. So basically, this circuit is like this. So I have resistor, this resistor, this resistor over here, and then I have one resistor over here, one more over here, and this is my circuit. Okay, and this is E, this is I, and these values are already given. So this value is given. This is 1 ohm. Okay, this is 6 ohm. This is 4 ohm. This is again 1 ohm, and here 2 amps current flows. This is again my 1 ohm, and now I have to find the value of E and I. So in this circuit, what I have to find is I have to find the value of E and I. So in order to find the value of E and I, so how do I go about this network? Is that first, let me see this part. Let's see this zone. Okay, I can say in this zone I have across this circuit 4 ohms and 2 amps. So I can say V is equal to I into R. So I can say that 4 into 2 is equal to 8 volts. So since this is here, there is 8-volt current. So that means this is a parallel network. So across this also there would be 8 volts. So the current across this I into 1 would be equal to 8 volts. In other terms, I value, that is my current value over here, would be equal to, suppose this is I, okay, this would be 8 amps. Now let me divide this KCL equation. This is I over here. Let's say that this current is getting divided into 2 points. Let this be I1, this be I2. Okay, let's mark this as a node 1. Okay, and another node is here, that is node 2. So I2 is entering node 2, and 2 amperes is leaving node 2, and another current that is following through this would be this. and let this be I3. Okay, so what I can say that I2 is entering node 2. Okay, at node 2, I2 is entering node 2, 2 amperes plus I3 is leaving. So I3 is leaving. So how much is I3? Just now I calculate the value of I3 as 8 amperes. So I2 happens to be 10 amps. So now in this circuit I2 happens to be 10 amps. So what I can say safely is that the voltage across this network would be 10 into 1. It happens to be 10 into 1. So this is 10 volts. Now 10 volts, and here we saw the voltage is 18 volts. Now I have this convention. Let me take a sign convention, current convention in this loop. Let me write this as, I have written this as 1, okay, 2, okay, 1, 2, this point, let this be 3, and these points are 4, 4, 4, 4, and let this be 5, okay. So I can see this in this circuit 1, 2, 4, 4. In circuit 1, 2, 4, 4, I can write my voltage rise is equal to voltage fall. So I can easily write this. So if I see the voltage rise, that is minus to plus is my rise, and I take it as positive, and minus to plus if my current is flowing in the opposite direction like this, and this is negative. I told you in the beginning this would be fall, this would be rise. So here I see this, the voltage across this network is my V rise. So I want the voltage across 6 ohm resistance. I say the voltage across 6 ohm resistor is V rise. Okay, voltage across 6 ohm resistor is V rise. Okay, that one value we got, and now you can see over here plus minus plus minus. Now the direction is like this, so there is a fall. So this is 10 volts plus 8 volts. So the total V rise that I am getting is 18 volts. So the current across 6 ohm resistance, that is I1, that would be 6 into I1 would be equal to 18. And now if I want to find the value of this current, that would be I1 would be 8 divided by 6 is equal to 3 amperes. Now I can find the value of I. So the value of I would happen to be at node 1, at node 1 over here. Current entering the node is I1 plus I2. So I found the value of I1 to be 3 amps and I2 value has to be 10 amps, that has been calculated here. So this happens to be 13 amps. Now I want to find the value of E. So I value we found, that is 13 amps. Now we want to get, now look at this circuit to get the value of 5144. So 5144 circuit, this circuit, that is 5144 is this circuit. Again, let us suppose this is current direction, E is the voltage rise. So E is voltage rise, okay, voltage rise, and rest is fall. See here, plus minus this is fall, plus minus this is fall. So over here you saw the over here the voltage due to this would be 13 into 1, okay, that is 13 is the I into 1 ohms, and over here we just now found the voltage to be 18 volts. So the total voltage would be 31 volts. So we fetched 2 marks. Very simple. If you had seen my lecture 1 and lecture 2, then you are able to do any problem, be it gate problem or whatever problem, but you have to be a little bit very much street smart with respect to this. Let's go for one more problem and let's understand how to go about it. So this is a very simple problem that has appeared in gate examination. So if on KCL, let's do this problem. So the problem on KCL, okay, if we have three current sources, if we are having three current, and these current denominations, I'll write down the problem. So this was question number 1. Let's go for question number 2. Yes, I'm creating a new whiteboard. This is question number 2. Okay, so I have current I1, I2, and I3 meet at a junction. Okay, junction means where more than 3 points are connected. If you are crossing a road also, you know this is a junction point. Okay, so it can be 3 more than 2. Okay, so here it can be 4 also. So at this junction point, this current I1 is entering Okay, so at junction means all the current I2 and I3. The summation of all the currents entering I1 plus I2 plus I3 happens to be 0. Okay, meet at a junction in a circuit. Okay, nice. In a circuit, all currents all currents are marked as entering. Okay, as entering the node. So he has already mentioned these are marked as entering the node. Okay, now what he says that if I1 is equal to minus 6 sine omega t milliamps, and I2 happens to be 8 cos omega t milliamps, find I3. So it's very simple. What you have to do is that from here I wrote I1 plus I2, so I3 would be equal to minus of I1 plus I2. So what you have to do, you have to substitute these values there and get the answer. So it will be very simple, and you have to have some trigonometric analysis for it. So that's what, when you were studying trigonometry, where it is getting applied. So here it is getting applied to calculate the current. See here, so I have this I3, I can write minus, okay, I1 value is given minus 6 sine omega t. Okay, minus 6 sine omega t plus of, okay, again I can write this minus. If I am taking common over here, I can write minus 6 sine omega t minus of, sorry, minus of 8 cos 8 8 cos 8 cos omega t. So once I'm writing these points, what I notice is that if I make it in a fraction, suppose if I take a value of 10 outside, and what I write is that I write this in terms of minus, and minus will be plus 6 by 10 sine omega t. Okay, and similarly here I do minus 8 by 10 cos omega t. Now if I know that my, what is 0.6, okay, uh, so if I have to take the value, you go to the calculator, and with the calculator, with the help of the calculator, you have to calculate the values. So if you will notice, if you will do cosine inverse of 0.8 by 10, you will get around 36.87. Similarly, sine inverse of 0.6, you will get 36.87. So herein what you can write is that if you take this value, okay, and this value, to get this 10 of, here you can write sine inverse of 36.87. okay, sine inverse of 36 sine sorry, this 6 by 10 would be sine inverse of 36.87 into sine omega t. Okay, minus, you will get the value of cos of 36.87 into cos of 36.87 into cos omega t. Now if you carefully notice over here, what we have to do is that, see, initially we did substituted this value of minus over here, and minus we did plus, but then here it would become again this minus will vanish and it will turn into plus if we have to do the same thing. So what we will do is that we'll keep the values like this. We take the minus 10 outside, so that we get this cos thing here, minus 10 cos 36.87 and cos omega t, and here it would be plus of sorry, here it would be again minus of sine 36.87 into sine omega t. So this is a formula for cos a plus b. So this is cos a cos b, this is what, cos a cos b minus sine a sine b. So this happens to be cos a plus b. So I can write the formula cos a plus b, and my answer to this would be minus 10 of cos omega t plus 36.87. So this is one of the problems that we have to notice over here. So then there is a very famous question that time and again comes, like is being asked. So let's do this question and wind it up this session. So we will again, and finally we'll do an R to R ladder. So these are three questions, all of them are from gate. So this question reads like this, okay. Two incandescent, two incandescent, two incandescent bulb are of are of 40 watts and 60 watt ratings, okay. These are two bulbs, there are 40 watt and 60 watt are connected. Now see, are connected, these are connected in series, these are connected in series, okay, across the mains, okay. Then it is asking which bulb will glow brighter, bu- which bulb will glow more. So a simple analytics, if you see this question for the first time in your mind, a simple thing will come. 60 watt bulb has having more wattage, so it must grow brighter, okay. So what we see is this is a voltage source over here, plus minus. So bulb, let this be as a resistive load, okay. So this bulb happens to be 40 watts, okay. This bulb happens to be 60 watts, okay, or vice versa. So which bulb will grow brighter? So this is the voltage, okay. Current through this would be same, okay, because it is connected in series, so current would be same. Now what about the power? So power inside the bulb depends upon the voltage square into R. So now you see the bulb here, if you notice here there would be VR1, here there would be VR2. So if you divide this voltage divider, VR1 would be equal to R1 R1 plus R2 into V, okay, wherein VR2 would be equal to R2, that is the bulb 60 watt. So VR1, let us write this is the 40 watt and this for the 60 watt, okay. This would be R2 R1 plus R2 into V. Now let's notice, see, if this is a constant power, constant voltage, so what happens? See, for a 40 watt bulb, V square by R. So R would be equal to V square by 40 watts, okay. And now R for a 60 watt bulb would be equal to V square by 60. So we notice if the voltage is constant, the value of R is greater for a 40 watt bulb. It is greater because in the inverse, whereas for a 60 watt bulb, the value of R is less, and the power dissipation, that for glowing it is I square R. So we notice that I value remains same in this network. So the R value for 40 watt is more. So R of 40 is more. I square into R of 60 is little lesser. So that means this 40 watt bulb will grow more brighter. 40 watt bulb will grow more brighter. So this was about these certain questions of gate examination. So let's solve some more problems. Like one more problem what I'm interested in. So these are some simple problems that time and again appear in the examination. So this is one more problem for you. So the RMS value of a half wave a half wave rectified symmetrical square wave of current of 2 amperes is. So the RMS value of the current for a square wave simple of 2 amperes is. So how do we go about this particular problem? See, if we see the formula for the IRMS value, so you can directly write IRMS is equal to what? 1 by T. So you should know this, 0 to T, okay, I square T dt. So here this is the half wave rectifier symbol would be like this only. So this is till here 2 amperes, then till here nothing, then like this it goes, okay. So this is 0 to T by 2 till T, and from T to 3T by 2, and so on it goes till 2T, and this is the thing. So here it is 2 amperes, so you can put this value, this would be 4, okay, then T, okay, T is 0 to T, 0 to T value 1 by T, okay, this is the square root of it. So what you get, 1 by T into 4, this is P minus 0, this is P minus 0, so something. Okay, so what T and T gets cancelled, so you are left with root 2. So this would be the answer for this question, root 2. So on a similar grounds now, what we have seen on a similar grounds, let's take one more problem, and let's see how we go about it. Suppose what I do is that I want to check your KCL knowledge, and I connect a series, a network like this. Okay, so this is also appeared in the gate examination. So I connect the voltage source over here, I connect one ammeter, okay, and uh, a resistance, one more ammeter, okay, and I connect an inductor. So inductor and ammeter, this is AC, and what I want is that now I want a current across current in this. So this is V, this is I. So usually what you will say is that this value of I has to be I2 and I3. But this is now in this form. This is now R plus JXL form. See, wherein your V value, you're drawing the voltage, and if you are having a resistance, okay, then your V and I value, this is V and I value, would be in phase. But if you are connecting voltage and if you are drawing an inductor, so voltage and current will have some angle between them, and this angle would be 90-degree angle. So when we are calculating this current, so let's suppose this be 12 amps and this be 9 amps, so we cannot directly connect this. So in order to calculate I, so this is basically in terms of 12 plus J9 form. So now 12 plus J9, the current value which you will get is in the form of 12 plus J9 in the polar form. If you want to get the magnitude of it, so this would be 12 square plus 9 square, that is, this is 144 plus 81 का whole square, so this is 225 का whole square, so this would be 15. And if you want this just magnitude, this is the magnitude. Now if you want the angle also, then it would be tan inverse of 9 by 12 or 1 by 3. So tan inverse of 1 by 3 you can do in the calculator. 1 divided by 3, you get 0.33, tan inverse, you get around 18.4 angle. Okay, so this is not a big thing. So this is one of the questions that has appeared in the examination. Now let's move to a new and versatile concept of R to R ladder, which we are interested. What is a R to R ladder and how we will go about it? Let's see this. So those of you who are new to the channel, please like, share and subscribe the channel, and please support us, and we'll be getting you with new concepts every day, and new uh, theories which you have never seen before, so that it's very student friendly, so that you understand all the concepts. So basically when we talk about the resistive ladder, so it's a combination of series and parallel networks. So if I have a voltage source over here, so in a resistive ladder I have a network that is this one resistance in series, then another in parallel. Okay, then I say another resistance in series, another in parallel, so another resistance in series, another in parallel, so on and so forth, it goes on. So this is the concept of this R to R ladder. So I can write this value, for example, it's my R1, this is R2, this is R3, this is R4, and it is a voltage source over here, R4, similarly R5 and R6. So this ladder network goes till here. So I can write this particular point over here as R2 n minus 2, and here it will be, see, here you can see the odd part is there, and here the even part of the network is connected in cascade, that is also called in series. And finally we have this R2 R2n that is connected up to n. So see, the analysis of resistive ladder, how do we go about it is, how to calculate R equivalent is, you go back from this R6, you see R6, okay, if you are seeing from R5 point of view, so you notice that if you have to move that, so to what you do is that let us find the equivalent ladder resistance to this end. Let us start from R6 and work backward towards the source. See, what happens is that the R6 will appear in parallel with the equivalent resistance seen looking into the dotted portion of the ladder. Okay, so what we can do is that their reciprocals can be added together. This combined resistance appears in series with R5. So you can see that 1 by R6 can be added in series with 1 by R6 plus R5. So the two may be added together, proceeding the same manner. So see, only till R6 if we are doing is that we will start with the, see, let's start here somewhere, okay, and 1 divided by 1 by R6, okay, plus is the network that is following. So this network can be added in series with this because this R5 is in series, okay, with a parallel combination. Here only simple node is there. So now you know that, okay. Similarly, what you can write is that, so this network again is in parallel with, okay, this 1 by, just now you wrote down, so this whole combination is in series with is again in parallel with 1 by R4. So again here you can write 1 by R4 plus, okay, so 1 by R4 plus, so this entire 1 by R4 plus till here, okay, is in series with R3, okay, is in series with R3. This entire network whatever you have seen till now, this entire network whatever till now you have seen is in again parallel with what, 1 by R2. So this again till here 1 would be in parallel with plus 1 by R2, which again 1 by R2, okay, and the whole network, see, 1 by R2, this whole network is in series with R1 plus the whole network 1. So in other terms I can write it like this for understanding purpose. R equivalent is equal to R1 plus 1 divided by 1 by R2 plus the other network, okay, this is 1 divided by R3, okay, plus 1 divided by 1 by R4 plus 1 divided by R5 plus 1 divided by R6 plus 1 divided by R6 and so on and so forth. Suppose let's do a problem, find the equivalent resistance of a three stage resistive ladder, okay, resistive ladder with R1 is equal to 12 kilo ohms, R2 is equal to 10 kilo ohms, R3 is equal to 30 kilo ohms, R4 is equal to 15 kilo ohms, R5 is equal to 20 kilo ohms, R6 is equal to 10 kilo ohms. Now if you want to find the R equivalent, straight away 12 plus 1 divided by 1 by 10 plus 1 divided by 30 plus 1 divided by 1 by 15 plus 1 divided by 20 plus 1 divided by 1 by 10, which would be 10 again, and this whole network is 20 kilo ohm. So those of you who enjoyed the session, who liked the session, please like, share and subscribe to our channel to receive videos. Already there are lecture series of basic electrical engineering, power system engineering. Soon we are be putting other subjects like control engineering and power system engineering, always there. Thanks for your love, support, love and support. Please share us and subscribe to it. Thank you very much, and bye for now. Thank you very much.